in this fourth example, we have the problem, and the problem statement goes like this. So the open loop transfer function of a unity feedback system is given by g of s is equal to k by s into 1 plus st, where k and t are positive constants or positive values. Now, by what factor the amplifier gain k should be reduced to reduce the peak overshoot from 75% to 25%? So this is the problem. So we need to find how to reduce, or what percentage we need to reduce the amplifier gain to reduce the peak overshoot from 75% to 75% to 25%. We know the effect of the peak overshoot. The peak overshoot should be always very less. So ideally I said zeta value is around 0.7, but in this case we are getting the 75% peak overshoot, and I am going to reduce that peak overshoot to 25%. So in the system we have k is amplifier gain. So amplifier gain is always tunable, then we can change the value of it. So it may be any value, but we want to find out the what factor we should reduce it. So this is some kind of a design problem where we are going to setting the value of my amplifier gain irrespective of the time constant. We don't know the time constant, that is 1 plus st, that is one infinite pole, one finite pole, 1 plus st. Your time constant we don't know, but still we could able to set the amplifier gain so that the system will reduce the peak overshoot to 75% to 25%. Now, how to solve this problem? So first of all, we know the relation between a peak overshoot and damping ratio. Your peak overshoot damping ratio are inversely proportional, which means when you want to reduce the peak overshoot, I need to increase the damping ratio. Okay. Now, so look at the first case where we have 75%. For example, percentage MP is 75%. My zeta value I am taking it as zeta 1. My amplifier gain k is k1. So 75%, I am just defining what is zeta and k. Zeta will be zeta 1, k will be k1. So 75% we know. So from the 75% I can find out the zeta 1. So let us see how to find zeta 1. So we know the equation for peak overshoot, percentage MP. So percentage MP is e power minus pi zeta by 1 minus zeta square under root into 100. So here we know the peak overshoot, but we don't know the zeta value, zeta 1 value. So this is 75% is equal to e power minus pi zeta 1 divided by 1 minus zeta 1 square into 100. So we will get it is 0.75. So e power minus pi zeta by zeta 1 by 1 minus zeta 1 square. So we have e power term here. Here it is 0.75. Then I can apply natural logarithm. When you apply natural logarithm both sides, and here you are going to get as minus 0.2877 is equal to, so we can simply cancel that e power term. The remaining terms will be minus pi zeta 1 divided by under root 1 minus zeta 1 square. Now I can square it. So when you square it, before that you can cancel minus, and when you can square it, when you square it you will get zeta 1 square, pi square zeta 1 square is equal to 0.0827 into 1 minus zeta 1 square. So here we can simple arrangement we can make it. So it goes like zeta 1 square is into pi square plus 0.0827 is equal to 0.0827, and from this you can find out what is zeta 1 square, and again we can find out what is zeta 1. Your zeta 1 is finally 0.0911. So this is a value for percentage overshoot of 75%. The similar calculations we can do for the second case where percentage MP is 25%. Now when percentage MP is 25%, I am going to define the damping ratio as zeta is equal to zeta 2, and similarly my amplifier gain is k is equal to k2. So we will try to find what is zeta 2 value for 25%. So straightforward we can write out 0.25 is equal to e power minus pi zeta 2 divided by 1 minus zeta 2 square. Then apply natural logarithm. Then again you just square on both sides. Then finally you are going to get zeta 2 value as 0.40368. So we know how to calculate zeta 1. We also got the zeta 2, and by using these two values, then you can find out by what factor amplifier gain can be reduced. So next, but we should know what is the relation between zeta and k. So if you know the relation between zeta and k, then you can find out by what factor k can be reduced. For that, let us look at so to find the relation between zeta and k, let us take the closed loop block diagram. Now I have g is the forward path transfer function, h is the feedback path transfer function, then input and output, and it is negative feedback. It is given that the open loop transfer function with a unity feedback, so h is equal to 1, g is given as k by s into 1 plus st. Now I can find out the characteristic equation from this. We know the formula. Characteristic equation is 1 plus gh is equal to 0. So 1 plus whatever we have, that k by s into 1 plus st equal to 0, it results in s into t square plus s plus 1 k is equal to 0. So we need to arrange this in a standard form. Therefore when you arrange it, s square plus 1 by ts plus k by t is equal to 0. Now this is the characteristic equation of the given system. We have the standard characteristic equation, s square plus 2 zeta omega ns plus omega n square is 0. So by comparing these two, then you can find out the omega n value, that omega n is under root k by t. Similarly, we can compare the second term, that is 2 zeta omega n is equal to 1 by t. So we know omega n already. By substituting this there, then you can find out the zeta relation. The zeta is equal to 1 by 2 root kt. So once we have the zeta relation, we know already what is zeta 1 and zeta 2. Let us take zeta 1 by zeta 2. When you take zeta 1 by zeta 2, then you can write the zeta 1 expression 1 by 2 into root k1 t. T is same only, we are not changing the time constant. Into again zeta 2, we need to substitute 1 over that it will come in the numerator, that is 2 into under root k2 t. You can cancel t, then you will get the zeta 1 by zeta 2 as under root k2 by k1. So we want to find k2 by k1. So k2 by k1 will be zeta 1 by zeta 2 whole square. All the values know. Zeta 1 is 0.0911, zeta 2 is 0.403. If we substitute and if we square it, then k2 by k1 is equal to 0.0509. Now k2 is 0.0509, k1 is the relation. But what factor your amplifier gain can be reduced? So the amplifier gain k can be reduced by the factor 1 over 0.0509. So that will be around 16.9. So this is a factor where the amplifier gain can be reduced to reduce the peak overshoot from 75% to 25%.